Right, so maybe we can just start. So we're a few minutes after the time. So welcome everybody to the Quasars and Galaxies Through Cosmic Time conference. So thank you very much everybody for attending. Thank you very much to all of the speakers, the poster presenters, and also the discussion moderators for a great week. As you have seen, we have a great lineup of talks and posters and discussions that will happen throughout today and Thursday. So before we start with the conference, I just wanted to acknowledge and thank all of the people that make this conference possible, and then give you some general information about the conference, so then we can move on to the talks. So this conference, to give some background, started as an idea from a joint project that it's being funded by Max Planck and ANID between Universidad Diego Portales in Chile and the Max Planck Institute for Astronomy in Germany. So with Manuel Aravena, we're leading the part in Chile, and Eduardo Bañados is leading the part in Germany. So originally, this conference, when we obtained the funding, this was at the end of 2019. We wanted to, of course, make it in Chile, presential, bring everybody here. But unfortunately, of course, the conditions have not allowed it. So we decided a while back to transition this into a fully online conference due to the pandemic. So I'm glad to see so many people connected. I'm glad to see there's been a great reception of this conference. So I should start by thanking all of the people that helped make this possible. And I want to start with the Science Organizing Committee. So I'm the co-chair of the Science Organizing Committee, and Jorge González Lopez is my other co-chair. Also in the SOC is Manuel Aravena, Eduardo Bañados, Caitlin Casey, Claudia Lagos, and Chiara Matsukeli. And want to thank all of them. Thank you very much for all the help, everything you did to prepare for this meeting. And in particular, I want to especially help Jorge González Lopez, my other co-chair, because it wouldn't have happened all of this without all of his help. So thank you very much, Jorge. In addition to the SOC, we had a group of graduate students that on one hand shadowed the SOC, so were with us throughout the entire process of how to create the conference and setting up all of the reviews and all of the abstract reviews, deciding on the program, and seeing how much chaos you can have before actually having a good conference still, how to deal with all of this chaos. And throughout this week, most of them will also be helping with the technical aspects of the meeting. So you will see them around connected on the Zoom. So it's Ana Carolina Poses, Manuel Solimano, Sofia Rojas, Tristan Lambert, and Liang Xi. So thank you, all of you, for all of your help and for all the help that you give throughout this week. As well as we also had a local organizing committee, which it made also a lot more sense when the meeting was thought to be presentially in Chile. But still, there were a lot of things to do locally, administratively. And so I want to thank, of course, Jorge and me were again the co-chairs of the LOC. Also, Manuel Aravena and Araceli Cifuentes was the coordinative administrator at the Núcleo de Astronomía de Universidad Diego Portales. So, some important information before we start, and then we can move on to the talks. So, we created a Slack workspace for this conference, and we sent all of you a sign-up link through email. If you did not receive it, please check your spam, but also if it's still not there, you can contact Jorge or me, and we can send you again the link to connect. In the Slack, you will find that there are channels for the discussion of the talks of each day, as well as for the general discussion of each day, and also for the posters. And for each day, All of the posters are already posted in that channel, so you can go see them, and also go into the Google Drive links if you want to see them at higher resolution. The full program of the conference is available on our website, as well as on the general channel of the Slack. So as a reminder, today we started at 8:45 a.m. Eastern time, and we're ending at 1:30 p.m. Eastern time. And between tomorrow and Thursday, we are going between 9 p.m. and 9 a.m. sorry, Eastern time, and 1:30 p.m. Eastern time. We're starting 15 minutes later than today. We will be recording all of the conference, and we'll be posting all of the recordings to the YouTube channel of the conference. It's called Quasars and Galaxies through Cosmic Time 2022, and it was also on the emails that we sent. Throughout the talks, you can ask questions either through the Slack on the proper channels or through the Zoom Q&A. And of course, even after the talks are done, you can keep asking questions through Slack so we can keep the discussion live. There will be invited, so there's 3 types of contributions throughout this the conference. So there will be invited talks, which are 30 minutes long, and then they have 10 minutes for questions. These are at the start of the first 2 sessions of each day. Then they're followed by contributed talks, which are 8 minutes for the presentation plus 2 minutes for questions. We also gave the opportunity to the people providing the contributed talks to also upload a longer talk. And for those who did, you can either find all of the links in the program in the conference website, or you can find them in the YouTube channel. Additionally, so we'll have posters. They are all available in the program, in the conference website, as I mentioned, but also in all of the Slack channels. So please go ahead, see them, and you can use the thread function on the Slack to start the discussion, to ask all of the questions. And then during the 3rd session of each day, the poster presenters were given 1 minute to present their slide, to get people interested and go see them on the website or on the Slack. And I think that's actually all I had. So just wanted to reiterate, thank you, and great thanks to all of the people that make this happen, and in particular to all of you that are connected, to all of the speakers for a great lineup of talks, as well as to all the poster presenters, and for the discussion sessions. Oh yeah, no, there was one more slide, sorry. And this is quite important information. So the discussion sessions are 40-minute long, starting at 12:50 p.m. Eastern time each day. So we'll be led by Ryan Hickox on Monday, Roberto De Carli on Tuesday, Chiara Mazzucchelli on Wednesday, and Maria Emilia De Rossi on Thursday. If you want to tweet about any of the great results that will be that appear during this conference, please use this hashtag so we can keep track of all of the things being shared from the conference. So hashtag QCAGT2022. And again, just want to reiterate, thank you to everybody. And without further ado, I don't know if there's any questions, but if not, we can start with the first talk of today. Let me stop sharing my screen. And I don't think there's any questions, but again, if there's anything, any questions about the logistics or any technical questions, just please go ahead and you can post them in the Slack. If there's nothing else, so I'm just gonna then give the control to the moderator of the first session, so Tanio Diaz Santos. So please go ahead, Tanio.
Okay, thank you, Roberto. First of all, thanks everybody for being here, and welcome to this first session of the conference. As Roberto said, we will have 5 talks. The first one will be given by Rodrigo Herrera Camus, an invited talk. And maybe you can start sharing. Yes. Perfect. So Rodrigo will talk about cold gas and dust in star-forming galaxies at a high redshift. So I think you can start, even if it's maybe minutes in advance, but I guess everybody's.
Then I get 2 extra minutes. That's good.
Yeah.
Okay, excellent. Well, thank you, Daniel, and thank you, the organizers, for giving me the opportunity to show, of course, not a super comprehensive view, but still some nice and recent results on the study of the high redshift universe, particularly looking at the cold gas and the dust. And we know this conference is about star-forming galaxies and quasars, right? So I'll be more on the side on the normal, typical star-forming galaxies in the universe, but I'm sure there will be plenty of very interesting talks looking at more extreme objects like the quasars. So I'm Rodrigo Herrera Camus. I'm a professor at Universidad de Concepción in Chile, in the south of Chile. And I'm also a group leader of a partner group between Universidad de Concepción and the MPE, in particular the infrared submillimeter group called the Baryon Cycle in Galaxies. And many of the results I'm going to present today are actually part of this 5-year collaboration. So as I was saying, this talk will focus on galaxy evolution, and in particularly one aspect of galaxy evolution, which is the evolution of the cold gas. We know that since the Big Bang and the way the universe has been evolving, there are some quantities that are key in terms of evolution, like the star formation activity, the stellar mass, the atomic gas, the molecular gas in galaxies, right? In this very nice plot by the paper by Fabian Walter, we see the evolution of these 4 key quantities. In the first panel, you see how the star formation rate history peaked at around redshift 2. The stellar mass constant, is increasing, and at about redshift 2, we have that we created around 50 to 70% of the stars we see today in galaxies. The density of the atomic gas is more or less constant across redshift, and the molecular gas you see in the last panel in blue actually trace very well the increase in the star formation activity in the universe. And in this talk, therefore, I would like to focus on these 2 components, looking at the atomics and the cold molecular gas at high redshift, understanding the evolution, the properties of normal galaxies in these particular 2 gas phases. Now, we've seen a lot of new and very interesting results, and we will see, of course, these results in many of the talks in this conference, thanks to 2 very powerful facilities that we have now to study the cold gas in the universe. On the southern hemisphere, we have ALMA, and on the northern hemisphere, we have the upgraded capabilities of NOIMA. And then if you look at the plot here on the bottom, we see that they allow us to cover a range as a function of redshift, which you see here on the x-axis, where we can actually obtain the dust continuum and different lines that allow us to trace not only the molecular gas, but also the multiphase gas in these galaxies. So from redshift 0 to about redshift 3, we can actually look at the CO and C1 lines of galaxies and study their molecular gas using them. There are these large programs, of course, that are part of ALMA, like the Lensing Cluster Survey or aspects that have provided very rich information on the molecular gas properties in at redshift 0 to 3. And there is also the FIPS and NOIMA 3D large programs, which are part of NOIMA, that also allow us to understand a lot more about the molecular gas properties of galaxies. If you go to higher redshift between 4 and 6, then we need to use the C2 line, because really looking at CO lines, it's very hard, it's very challenging, and you usually can only observe the CO lines that are higher transition. So don't trace very well the cold gas component of galaxies. And in that sense, the Alpine survey, which is a sample of about 100 galaxies observing C2 line emission between redshift 4 to 6, has played a critical role. At the end of this talk, I would like to introduce a new ALMA large program that we have started looking precisely at normal star-forming galaxies at redshift 4 to 6, which is called Crystal. It stands for C2 Resolve ISM star-forming galaxies with ALMA, and essentially will provide a kiloparsec view of star-forming galaxies at this redshift in situ line emission, and dust containment. But I'll talk more about that at the end of this talk. Also, I will focus on this talk mainly on results of galaxies that are actually on the main sequence. So the main sequence, just in case, I don't know, somebody is not very familiar with the term, it's really when you look at the distribution of galaxies in the star formation rate, the stellar mass plane, the sequence of star-forming galaxies. Galaxies above the main sequence are those that we consider starbursts, and galaxies below the main sequence is those that we consider quiescent or passive. And of course, there is a connection between these three groups. And in this talk, I'll try to focus as much as possible on typical normal galaxies at high redshift. So let's start with the molecular gas, which is key because it's the fuel for star formation. And we really, if you want to understand how galaxies form and evolve, we need to understand, on one hand, what is the molecular gas content of high redshift galaxies, and also how does the molecular content or properties like the gas fraction or the depletion timescale, which essentially also can be considered the star formation efficiency, vary with redshift. Two typical ways of actually studying the molecular gas in galaxies are the dust and the CO and atomic carbon lines. And the C1 lines is thanks to ALMA, is now more common also to study the gas in normal galaxies. So when you're using the dust, what is very interesting is that hopefully you do get a very good estimate of the dust mass, which you can do if you fit the SED. And then by assuming a dust to gas ratio, which essentially, of course, there are assumptions that need to be made and depends on the metallicity of the galaxy, you can convert that dust mass into a gas mass or ISM mass. There is also the method that has been very exploited by, for instance, the papers by Nick Scoville, which usually use only one measurement at the Rayleigh-Jeans tail of galaxies. The 1 millimeter, for instance, at a frequency, at a wavelength of 1 millimeter, which essentially also allows us to get an estimate of the dust mass of the cold gas and then convert that into a gas mass. So that's one method, using the dust. Using the lines, of course, also has it also has some challenges in the sense that you can observe, for instance, the CO line in one galaxy, but then you need to apply a conversion factor, right, to go to a molecular gas mass. And we know this conversion factor is a strong function of the metallicity of the galaxy, in the sense that as the metallicity decreases, the CO line traces less and less of the molecular gas in the galaxy. Now, we are in an era where we have more than 1,000 molecular gas measurements of star-forming galaxies between redshift 0 and 4 by combining the dust and the line emission of these typical star-forming galaxies. And what I would really like to look first is this molecular gas fraction evolution as a function of redshift, which is you see here on the left panel, and then the molecular gas fraction, which is the ratio between the molecular gas mass and the stellar mass of galaxies, as a function of the separation from the main sequence. So first, we see a strong evolution of the molecular gas fraction of typical star-forming galaxies, going from redshift 0, which is just a few %, up to redshift 2, where we see an equal amount of molecular and gas mass in galaxies. In terms of the separation from the main sequence, we also see a strong increase of the amount of molecular gas relative to the stellar mass in galaxies that are, for instance, above the main sequence, in the sense that galaxies, starburst galaxies that are 50 times above the main sequence have molecular gas fractions that can be up to a factor of 6. If we look now at the molecular gas depletion timescales, which is the inverse of the star formation efficiency, and again, in the first panel, comparing as a function of redshift, and in the second panel, as a function of depletion, as a function of the separation from the main sequence, we see a very shallow evolution of the depletion timescale as a function of redshift, which is, in this case, set as 1.2 gigayears, and the dependence with the redshift is only to the power of -0.6. On the other hand, we see a strong dependence of the depletion timescale or the star formation efficiency with the separation from the main sequence, in the sense that galaxies, starburst galaxies that are 50 times above the main sequence tend to have depletion timescales or star formation efficiencies 5 times higher than normal main sequence galaxies. So in summary, what I would say is that we do observe a strong evolution of the molecular gas fraction with redshift, which essentially is showing that the molecular gas reservoirs of galaxies, in this of normal star forming galaxies, are tracking the evolution of the cosmic star formation activity. And then we see a kind of shallow or not so high evolution of the depletion timescale as a function of redshift, which is showing us that probably the star formation is driven by similar physical processes at high and low redshift. I would like to quickly highlight, and I'm not going to go into detail, but quickly highlight these results by two junior scientists. One of them is my former master student. She graduated now, Catherine Enriquez Brocal, who published this very nice paper of looking at the molecular gas properties of a massive main sequence galaxy at redshift 2, where we had plenty of CO and C1 lines to actually model the physical properties of the molecular gas. And also this paper by Manuel Solimano, who I know is participating in the conference, and but I think it's not talking about this in particular, that is showing how to extend the scaling relations that I just showed you to the kind of intermediate and lower stellar mass range. So please, I really invite you to check these papers if you're interested in the molecular gas content of normal high redshift galaxies. Now, what about redshift greater than 4? How to study the molecular gas or the cold gas of galaxies that are redshift greater than 4. Of course, CO is one alternative, but again, it's very challenging, it's very difficult. It can be achieved with, for instance, JPLA, but it's very expensive and it's very hard. The one tracer that we have available at redshift greater than 4 is the C2 line, which we know is one of the major coolants of the interstellar medium. So in an interstellar medium, in thermal equilibrium, you would expect that the amount of heating that is coming from the star formation and the amount of cooling, essentially, of the system that is mostly via the C2 line are similar, are comparable. So you would expect things like what we observe with Herschel. You see a nice tight relation between sigma C far and sigma C plus. So the cloud points here is Kingfish, and then the galaxies here on top are actually from the gold sample. And Tanio, the moderator of this session, is actually the leader of these papers looking at the ULIS in C2 line emission. Now, there is a tight correlation, of course, also between the star formation rate and the molecular gas content of galaxies, which we know as the Kennigat-Schmidt scaling relations, right? So this is one very nice result from the Alpine survey. We actually used that connection to really extend this molecular gas fraction measurement in redshift, going beyond redshift 4, as I just showed you before. And what they find is that the molecular gas content of main sequence star-forming galaxies between redshift 4 and 6 is comparable to that we observe at redshift 2, and it's about 1. Of course, using C2 as a tracer of molecular gas, comes with different assumptions, and we know C2 is really tracing different phases of the gas from the atomic to the ionized. So this is something, if you want, we can discuss more in the time for questions. Now moving to a different but very important topic again at high redshift is the study of galactic outflow, because they really shape galaxy evolution, and we really want to understand what is the incidence of these outflows, and if these outflows are present in these high redshift galaxies, how massive and powerful they are, and essentially what is their role, for instance, suppressing the star formation activity or enriching the medium around galaxies. Now, there are few considerations that we need to have in mind. One of them is that gas outflows are multi-phase. So essentially, we do find gas that is being expelled out of the galaxy in the atomic, in the ionized, in the molecular phase, covering a wide range of scales and a wide range of temperatures. And second, we know that outflows are ubiquitous in massive star-forming galaxies at high redshift. So in this plot that I'm showing here from this review by Natasha Forster-Schreiber at MPE and Stein-Woods, we see that as a function of in the x-axis we have stellar mass, and in the y-axis we have the offset in the main sequence. So we do see that the incidence of AGN-driven outflows, which you see here in color, increases as a function of stellar mass, and then galaxies that are massive very frequently are driving outflows. So of course they have an effect on their evolution. Now, going back to the local universe to understand and kind of study these outflows in detail, if we look at ULIRGs, which are not main sequence galaxies, of course, but are those the ones that we can actually characterize very well. Like the one I'm showing here on the left, which is just a merger of these two systems. And if we look at the outflow mass, which you see here in the top panel in the molecular ionized atomic and multi-phase gas traced by C2, and you look at the mass outflow rate, which is the comparison between the mass loss, the mass loading factor, which is the comparison between the mass loss rate or mass outflow rate and the star formation rate. What we find is that in both cases, these are dominated by the molecular phase. And the only actually phase where we reach mass loading factors that are much greater than 1, which are the ones that sometimes simulations need to actually quench the star formation activity in galaxies, are actually reached here on the molecular phase. Now, this diagram or plot, of course, is missing one very important phase, which is the very hot gas, which can also play a very significant role in transforming galaxies, but observation, and this is what we have in hand. And there is also a very nice paper by Fletch 2021, where you can check. There is a comparison also as a function of gas phase of the outflows in ULIRGs, in ultraluminous infrared galaxies. Now, in order to test this and to understand what is the composition of outflow at high redshift, we actually look at one galaxy from the main sequence, a massive galaxy called CZ400-528, which we know has an AGN. Is a main sequence galaxy, and this AGN is actually driving a powerful ionized outflow that we study using BLT Symphony, and that you see here in white, essentially showing the H-alpha broad component of this galaxy with an ionized mass outflow rate of about 50 solar masses per year. So we actually went and look at this galaxy using ALMA, to combine that with the Symphony data that provide also the ionized gas information of this galaxy. We detected the molecular gases, which of course with high signal to noise, because this is not what we were after. We were really looking at the molecular gas component, which we detect extending in the northwest direction for about 8 to 10 kiloparsec. And then it's especially coincident also with the ionized gas outflow of the galaxy, and both of them going in the minor axis direction, similar to what we observe in local galaxies such as M82 or your typical, or I don't know, ATC 253, like the prototypical outflow. In terms of the dominance of one phase over the other over the outflow properties, we find that both the mass and the mass outflow rate in this galaxy are dominated by the molecular phase. And as you see here in this plot, which is comparing the mass loss rate of the molecular and the ionized phase compared to the star formation rate of the system, we find that the mass outflow rate in the molecular phase is about 2 times the star formation rate. So really, if we do a very simple back of the envelope calculation for a massive galaxy at redshift 2 like this one, we would expect a mean accretion rate of about 200 solar masses per year. If you compare then the mass that is coming in versus the mass that is going out, or the molecular gas is being depleted either by being ejected by the outflow or consumed and transformed into stars by the star formation activity, we find a balanced terms of 0.6. And then using this, the simulations by Sandro Tachela, you find that the rate of change of distance from the main sequence for this particular galaxy is about -1 dex per gigayear. So essentially that shows that and suggests that if this galaxy continue having an outflow of this strength in about 1 gigayear, should move from the main sequence at redshift 2 going down to the realm of passive quiescent galaxies. So the outflow has an effect, of course, on quenching the star formation activity in this galaxy. And I know there will be plenty of other cases shown in this conference, looking at powerful outflows in different phases, but I just wanted to highlight the importance of looking at the molecular phase in these systems. Now, what about cold gas outflows at redshift greater than 4? Well, this has been very challenging to obtain for normal star-forming galaxies. One very nice result that we now have, thanks to the Alpine survey, is that if you actually stack the C2 transition observations of the most star-forming galaxies in Alpine, you detect this broad wing of gas that signals the presence of an outflow in these galaxies. And then if you look at the radial profile of the emission, so essentially you see the normalized surface brightness on the y-axis as a function of radius, we find that in the case of galaxies which are in the high star formation rate group of Alpine galaxies, the C2 light emission is more extended, much more extended, actually 15 kiloparsec. And this is interesting because, that was a question. It's interesting because what it's showing is a potential connection between the outflow in the central part of the galaxy and the extended emission in the galaxy that you see here goes up to 15 kiloparsec. Now, this is for stacking, right? This is stacking because you really need a high signal to noise to really detect the wings in these systems. So one case where we actually tried to do this for a single galaxy was looking at this particular system we chose called HC4, which it's a galaxy that has been observed before, was part of an early paper by Peter Kapak in 2015 as HST restrained UV data. It's interesting because it's not interesting in the sense that we chose one galaxy that is actually a main sequence galaxy, typical galaxy, as you can see here on the star formation rate stellar mass plot. And we observed very deep, high spatial resolution, about kiloparsec scale resolutions of this galaxy using ALMA. You see the nice detection here on the right. And what we actually find is that if you look at the minor axis in the direction of the minor axis of this galaxy, we do find an outflow signature in the central region that is going in the direction of the minor axis, and it's similar to what we have observed in other galaxies with an outflow that are much nearby to us. This was a surprise. I mean, this galaxy was not targeted as a galaxy with an outflow, but of course, when you look at these galaxies at this redshift, you would expect that if they have high enough star formation rate in the central part of the galaxy, you would expect to detect the outflow if you have enough signal to noise. The outflow velocities in this particular galaxy are consistent with those measured in other main sequence galaxies. In this particular case, I'm comparing the outflow velocity in HC4, you see here in yellow, with the outflow velocity scaling relation between sigma Cephar and the outflow velocity observed in main sequence redshift 2 galaxies, and it is consistent. Also, if you look at the mass loading factor, so you compare the mass outflow rate with the star formation rate as a function of sigma Cephar, and in green you see the stacking of atomic gas outflows by Roberts-Bolzani. We see that the mass outflow rates of HC4 are consistent with what has been observed in the local universe. And most importantly, if you look at the mass loading factor on a global scale, so you compare the mass loss rate versus the star formation rate of the whole galaxy, you find a very modest mass loading rate of about 0.5. But then again, thanks to the nice, beautiful resolution of the survey the observation of this particular galaxy, if you look at the central region and now compare the mass outflow rate to the star formation rate of the central region, you find a very strong mass loading rate that can go from 3 to 6. And of course, uncertainty is because you need to compare the C2 luminosity into a gas mass, and of course there are assumptions that need to be made. But I guess the point here is that something that can actually look like a modest mass outflow rate and on global scales can actually be a powerful outflow if you compare that in result observations. And in this galaxy, comparable to what has been observed in the stacking of the Alpine, we do see an extended C2 emission, or what you can call halo maybe, that extends beyond the dust, beyond the UV continuum disk, and that can be connected with the outflow. Essentially, the outflow essentially driving this gas and heating this gas around that can then be observed with the C2 line emission. So finally, in the last 5 minutes, I really want to look at the kinematics of galaxies, and because these are super important. I guess one of the most important questions we have right now in this particular field is like what are the demographics, what is the kinematic status of normal main sequence galaxies of high redshift, what is their level of gas turbulence, what is their dark matter and baryonic content. So we know that the intrinsic velocity dispersion of galaxies increases as a function of redshift for both ionized and the atomic and molecular gas. And this is, of course, consistent with the increase as a function of redshift of the molecular gas fraction and gravitational instabilities of these galaxies. There are two examples that I would like to show at redshift 1 to 2 that are very beautiful because these are very deep observations. In the first one that I would like to show is this deep H alpha and CO map of a star-forming galaxy at redshift 1.4, where you obtain a beautiful rotation curve for both tracers, the CO and H alpha, and they agree very well. And if you model this rotation curve and the velocity dispersion profile, you get a dark matter fraction that is low within one effective radius. And then we just obtained this beautiful molecular gas map of a main sequence galaxy at redshift 2 called BX610. So on the top right, you see the molecular gas component, the moment one or velocity map. And this is the result of 24 hours of integrations with ALMA, reaching a resolution of 1 kiloparsec. So this is a very, or probably the most, maybe the deepest map obtained at this redshift for a main sequence galaxy. And we have an equally deep map using BLT Symphony-AO, so essentially providing the ionized gas kinematics and combining the molecular and the ionized, the very nice sensitivity we obtain, plus the HST morphology, which you see here in the white contours. We will be able to study in the future not only how this galaxy is rotating, but any deviations from a rotating disk, and hopefully any deviations in the center, for instance, gas that can be radially transported to the central part of the galaxy. And we should be able to see that in the residuals after we subtract a rotating disk kinematics. Now, what to do at redshift beyond 4? It's very hard, of course, using the CO lines, but again, the C2 lines come to the rescue. And we have seen in the past beautiful C2 line maps obtained of main sequence redshift galaxies in the C2 that actually show rotating disks even at this very high redshift. As you can see here, this paper by Milman in 2020 and Renske-Smith in 2018 for these two redshift 7 systems. So for the one galaxy that I was showing you before, HC4, we have the velocity field and the velocity dispersion profile in this figure here. And based on a morphokinematic analysis, we find that there is a regular, smooth rotating disk already in place at redshift 5. A beautiful rotation curve that is starting to drop at about 1 arcsecond, which corresponds to 2 times the effective radius of this galaxy, and a centrally peak velocity dispersion profile. If we model the kinematics of these galaxies using a code called DismalPy, what we find is that a high intrinsic velocity dispersion profile that is consistent with the cosmic evolution. And this high velocity dispersion profile is driven partly by star formation activity, but really, according to models, for instance, by Kronholz 2018, you cannot reach this very high level of intrinsic dispersion if you don't have radial gas transport that is playing a key role here. So this high velocity dispersion is consistent with the evolution that we have observed for main sequence star-forming galaxies at lower redshift. In terms of the gas content of this galaxy and the dark matter and baryonic content, we find that on galactic scales, HC4 is dominated by baryons, as you can see here, and this low dark matter fraction within one effective radius that you see here as a function of the circular velocity, it's about 40%, and is comparable to what has been observed in massive main sequence galaxies at redshift 1 to 2. And it's interesting because HC4 is massive enough to think that at redshift 2 should become a massive star-forming galaxies at redshift 1 to 2. And then at redshift 0, these galaxies should become probably an early type galaxies with an even lower dark matter fraction. So it's interesting to know that at redshift 5, the dark matter fraction of these galaxies appears to be already in place in its way to increase the mass and then be at redshift 2 a massive main sequence galaxy. So for typical star-forming galaxies, and this is just a few minutes that I have left for the future, for the molecular gas and galactic outflows and kinematics, we are starting to live in a very golden era in the sense that we have ALMA that we can use to study the cold, gas, and dust, HST to look at the rest UV and of course stellar mass, and JWST, which will allow us to do a very, very, of course, detailed study of the ionized gas. So this will allow us to actually get a very detailed study of the gas, the dust, and the stars on kiloparsec scales in these galaxies. So this is what I would like to introduce the crystal survey. Tanyo, I think I have a few minutes left, right? So I can...
one or two, yes.
One or two, excellent. So that's enough. So the crystal survey, it's an ALMA cycle date, large program that we have started, and Jorge González López and Manuel Aravena's copies are very involved in this project. So just one slide. This is to look for, to observe in C2 and dust continuum emission, 19 main sequence star-forming galaxies at redshift 4 to 6. It's 140 hours of band 7, and the goal is to spatially resolve these galaxies on kiloparsec scales. All of these galaxies have HST imaging, and about 50% of them will be observed by JWST in the first year of operations. We just got observations from a part of the observation because the crystal is a combination of extended and compact array observations. So we just got the extended component of one of our galaxies that I'm showing here. And I mean, we made this plot yesterday because we really got the first delivery of the data a few days ago. And I mean, we're very excited because what Crystal will do is to really provide, provide key constraints on the kinematic, the outflows, the morphology, and the interstellar medium of galaxies. Essentially, it will be a survey of gas, dust, and stars on kiloparsec scales in star-forming galaxies at redshift 4 to 6. So I really want to thank you for the opportunity of giving this talk. And I really hope you enjoy the conference. And in the future, if you can visit Concepcion in Chile and see this beautiful mural we have on campus, you're very welcome. Thank you.
Thank you. Thank you very much, Rodrigo. Very, very nice talk. We have a few questions in the chat, but if anyone wants to ask them verbally, they can raise their hands now. Otherwise, we can start by the questions in the chat. So, well, the first one is from Paulina Lira, and she asks, is it common that the molecular outflows are more powerful than the ionized outflows? And what is the mechanism behind this behavior?
Yeah, so if I go back, this is at least what we observe in units, where you see that both in terms of mass and the mass outflow rate, the phase that is actually dominated is the molecular gas. Essentially, what happens is that there is, I mean, but this is, of course, depends on the assumptions. I mean, to get a molecular gas mass outflow, to get the molecular gas mass of an outflow, you really need to assume an alpha CO, which we believe we probably are not doing that bad. But for the ionized, you need to assume an electron density. And I know there is debate on what is the electron density of actually the ionized gas in outflow. So this value can go up. But for like standard assumptions, what we find is that at least in Euler's, what dominates is the molecular phase. And then what happens is that they tend to have comparable velocities, at least observationally. Again, it's sometimes hard to define the outflow velocity for these different tracers. And so that translates into mass loading rates that are actually higher in the molecular phase. But essentially, this all comes to the fact that it appears that the mass on this outflow is dominated by the molecular phase, at least in Euler. So I have a student now that is doing a similar exercise for normal star-forming galaxies using the edge sample. So we should get also a new estimate now for more normal galaxies, but that's working in progress.
Okay, thank you very much. Ryan Hickok, thanks you for a wonderful and really clear talk. And he's curious about the role of star formation driven outflows in quenching. He says since the outflow rate is connected to the star formation rate, one might expect the outflow rate to decrease as the molecular gas reservoir of the galaxy is depleted. And he asks if this impacts how long it would take for a galaxy to become fully passive, and whether black hole feedback be necessary as well to achieve it.
This is a very interesting question, because essentially it's all connected. In a way, we are ejecting the gas from the galaxy, but not all of these gas, that's another important quantity to try to estimate what fraction of that gas will actually permanently escape the galaxy and what fraction will be actually recycled into the disk. And once it's recycled, can this gas that is, accreted into the disk actually go to the center and continue fueling a star formation in the AGN? The first part about the radial transport of gas is something that we're actually trying to do now with these very deep observations of the molecular gas in galaxies, to really try to, look at the radial transport of gas that actually can fuel future episodes of star formation. And to me, I know there are some talks in this conference about this, about the transport and the recycling of gas. It's not clear to me what's really the time scale of this gas that, stay in the CGM, that go back, but of course it will depend on that time scale. I think what is really the role of the outflow quenching the star formation activity. So there are different processes that are connected in the Barnum cycle. Unfortunately, observationally, maybe we don't have a still very strong constraint on each one of these pieces, but we're definitely working on it. So I would say it's complicated, it's hard. At least this is one step forward in the sense that characterizing that, yes, the molecular phase is important, but then to really look at, what is the lasting effect on the star formation quenching, it's hard. And what I'm showing here was just a very simple toy model, which has a lot of assumptions. And in this case, for an AGN-driven outflow, you are able to quench the star formation activity in the scale of 1 gigayear. But again, it's complicated.
Okay, thank you again. One more question from Ji Wang. He thanks you for the interesting talk and asks, could you please talk more about the uncertainties and assumptions that go into using C+ to trace the molecular in ionized gas, comparing with neutral carbon?
Yeah, so the thing with the C2 line is that it's a multi-phase tracer. It's tracing the ionized, the molecular, and the atomic phase, because the ionization potential of carbon is below the ionization potential of hydrogen. And then it's a collision. The C2 ions get collisionally excited by these atomic or molecules, atomic gas or molecules. And of course, how bright your line will depend on the density of the gas and the temperature of the gas of your collisional partner. So if you actually advertise, if you go to my 2021 paper, I actually in the appendix explain in detail what are the assumptions that go into the calculation and how assuming different characteristics of the gas that is in the outflow being ejected essentially change the mass of the gas that is calculated. But again, so you need to assume what is the density, what is the temperature of the gas, and then go from there to convert from the luminosity to the mass. So the uncertainties can be big. And as I mentioned in the appendix of the 2021 paper, you can find all the detail. Thank you for the question.
Thank you, Rodrigo. One question more from Ilsan Young. She asks, how realistic is that this extended C+ halo might be due to accretion from the circumgalactic medium and not to the outflow? And she further asks, are these extended C+ emission for high redshift galaxies in general also seen in low redshift galaxies with similar star formation rates? So you can distinguish between these two scenarios?
Yeah, we actually, so this is one of the, to me, one of the most exciting results of these new C2 observations of high redshift galaxies is to really find this very extended component of C2 line emission. And what is behind this extended emission is actually not only outflows, as you said, can be the inflow of gas, can also be maybe in situ star formation that is happening, that is essentially heating the gas and is cooling by C2, and can be actually gas that was ejected by the outflows, or can be a combination of, or can be also unresolved, for instance, satellites that could be living there, and essentially can be a combination of all these scenarios that I just mentioned. And we believe that Crystal, our launch program that we are starting now, in a way will be very important to distinguish between these scenarios, because we will be able to actually look at the extended emission, but we will also have the resolution to actually look and, for instance, search for the source of this extended emission. I don't know if you're going to have the definite answer, but that will definitely be a step forward. And regarding extended CO2 emission in low redshift galaxies, I mean, I don't have, maybe, I mean, Tanya is also a C2 expert, can help me, but except for NGC 6946, which was a paper by Sue Madden in like 1993, which you see this nice extended halo of C2 emission that is tracing the atomic gas. I don't know of any other example where you actually can look at distinguished TS scenarios. Of course, in these galaxies, there won't be a strong accretion of gas from the cosmic web, so it's different. But this is a very nice question, because it's definitely one of the reasons why we are starting the Crystal project with Alma.
Thank you very much. And I think we are over the limit for the 10 minutes for questions. So there are a couple of two more interesting questions posted in the Q&A by Lev de Bolgard and Sebastian Lopez, that they will be copy-pasted into the Slack channel, and maybe you can answer them there.
Yeah.
So thank you once again, Rodrigo.
No, thank you, Tanya. I'll stop sharing. Thank you.
So we can move on to the first contributed talk of the session by Lucia Guaita. Maybe you can start sharing. Excellent. Perfect. So Lucia is gonna talk about the tomography of the environment of a very interesting galaxy at redshift 5.3.
Yes, thanks a lot. So this is a bit of an outline of what I'm going to say. I want to talk about this field, which is around OzDES. That's a submillimeter galaxy at redshift 5.3. Submillimeter galaxies are expected to be progenitor of very massive systems at lower redshift. So the aim of the study was to try to find any sign of interaction of a merger onto the SMG to try to support this hypothesis. So I will talk about the synergy of the data that we have. We have a CO and C+ emission, and I will focus on optical observations, in particular on the Lyman alpha detections in this field. The escape of Lyman alpha photons are related to the amount and the kinematics of the H1 gas in galaxies. So I will try to show some analysis of the spatial distribution of the Lyman alpha emission and some modeling of the spectral distribution of the Lyman alpha emission that can give us information on these neutral gas parameters. And then I will give some take-home points. So since 2011, we know that this region is in overdensity because around the SMG, two Lyman membrane galaxies were observed within 12 kiloparsec, and there were also 10 other Lyman membrane galaxies found within 2 co-moving megaparsec. The observation that we have so far are on the molecular gas, so there are CO detections in this region, and also ALMA detection of the C+. And here you can see an image of the MUSE mosaic data cube that we also have at the wavelength of the Lyman alpha emission at redshift 5.3. In the entire area, we found 10 Lyman alpha emitting sources that are represented here with these green and red contours on the RGB image. And the number of these sources in this area confirm the overdensity. We found more point-like emission and also an extended emission towards the submillimeter galaxy. In this slide, you can see the CO emission and the C+ emission, which were found to be quite compact, and the Lyman alpha emission, which is instead extended. So we have in this area around the SMG and the Lyman membrane galaxy just on top of it, an extended emission that has 2 peaks, more or less at the position of the SMG and the LBG. The one at the SMG is offset with respect to the center of the C+ emission, and there is also a tail going to the south. And on top of the LBG, we have an emission that is more elongated towards the north, up to 80 co-moving kiloparsec, and also tilted. And then there is also some emission in between the SMG and the LBG. We say that this is like a bridge of Lyman alpha emission, which is tracing a bridge of H1 gas between the 2 galaxies. And it's also in the region where a low significance but extended emission from the C+ observation were found. Here you can see the 1D spectrum of the integrated emission in this area. We have a main peak and a tail in the Lyman alpha spectrum, and the main peak is offset with respect to the C+ systemic redshift, and based on the modeling of Lyman alpha emission, this is related to the kinematics of the H1 gas. Here you can see the Lyman alpha channel map that shows the Lyman alpha emission at every wavelength where we have the detection. So basically on top of the SMG, we have a kind of bright emission at all the wavelengths where we have a Lyman alpha detection. And the bridge emission I was talking about before is concentrated between 200 and 500 kilometers per second with respect to the C+ emission. And this range on velocity could be related to the range of kinematics of the gas that we have here, and also a range in H1 column densities. At the peak of the main emission, we have extended emission to the south and to the north, which is more confined in wavelength. And then we have an elongated emission starting from the SMG and going towards a galaxy to the south, which is also at redshift 5.3. This partial distribution reminds the Lyman alpha emission, which is expected by a merging event. Then we use the ZELDA radiative transfer model to predict the spectral distribution of the Lyman alpha photons, given some values of the H1 column density and the kinematics. We fit the entire emission I showed before, also dividing the main peak and the tail, and also we try to fit the emission only coming from the SMG, from the bridge and from the LBG, to try to derive some picture of what's going on in this Lyman alpha extended emission. So basically, yes. Yes. So basically, we found that on top of the SMG, the Lyman alpha main peak is broad, and this could be related to a large value of the H1 column density. And this is also the case where the bridge is located and where the LBG is located. And also there is a tail, which indicates that the kinematics of the gas could be related to an outflow of up to 800 kilometers per second. So basically, we have H1 column density of the gas, which are consistent with a gas that is efficient in scattering Lyman alpha photons, where the Lyman alpha emission is brighter, and also in outflows, which could be related to the starburst of the SMG. And the spatial distribution of the Lyman alpha photons instead is consistent with the presence of interaction of the SMG with the two galaxies, one on the top on the north and one on the south. So this could be related to phenomena of accretion onto the SMG we wanted to find evidence of. Based on the surface brightness of the Lyman alpha nebula, we can estimate the dark matter halo mass, and from this predict to which kind of cluster this protocluster could evolve. And it's a cluster of 10 to 14 solar masses, which is 1 order of magnitude lower than that is expected for protocluster that contain more than one SMG. So basically, we use the MUSE observation, in particular to trace the Lyman alpha emission in this region. We found an extended emission on top of the SMG, and studying the spectral distribution of the Lyman alpha photons and the synergy with the previous CO and C+ emission, we found the evidence of interaction and merger onto the SMG that could be related to the fate of the SMG to a more massive system, to lower redshift, and also gives information on the fate of the protocluster. Thank you.
Thank you very much, Lucia. Very nice talk. I don't know if anyone wants to ask any question live, or we have, it just appeared one question from Cristobal Moya. He thanks you for the very nice presentation. He didn't understand the meaning behind the green and blue fits when you showed the CELDA results. Are you fitting two components there?
Yes. So since we saw that the Lyman alpha emission, when we integrate all the spectrum, contain a main peak, but also a significant tail, we wanted to see where the photons from the tail mainly were coming from. So we tried to extract, in particular, the spectra on top of the SMG, on top of the Lyman alpha emission main component, main peak, let's say, of the SMG, and of other parts of this nebula where we had enough resolution to see if we could disentangle the places that were most contributing to the tail and to the main peak, and the properties of the H1 gas that could produce this tail and this main peak. So we found basically that, for example, in this region here, we have, so the SMG is here, and the main peak emission is over here. And over here, we found that the Lyman alpha profile is consistent with a region with very high column density and very high velocity outflow. And this outflow could be consistent with the presence of the starburst onto the SMG.
Thank you.
Yeah, I hope
Thank
I
answered
the question.
I think, yes, we had time for this question. If there is any other, you can always put place them in a Slack, and I'm sure Lucia will be happy to answer.
Yeah, of course.
Okay, we can move on to the next talk by Giustina Vietri. Can you share the presentation? Excellent. Excellent. So Justina will talk about the discovery of a powerful and variable ultrafast outflow in a redshift 3.6 quasar.
Can you see the screen?
Yeah,
okay.
we can see your presentation.
Thank you. Yes, so hi all. I will talk about the discovery of broad absorption line ultrafast outflows in a quasar at redshift 3.6. So just briefly, we know that the agent feedback is invoked to explain various observed properties of local massive galaxies. And for example, for the luminosity function, we know that the theory predicts too many massive blue galaxies than observed, and the agent feedback help in reducing discrepancy between theory and observation. We know that the agent feedback acts through agent-driven outflows, which are capable of remove or eating up the gas and quench star formation. So theoretical works talk about a two-phase mechanism for this feedback. In particular, we have an ultrafast outflows, which is launched and accelerated out by radioactive forces from the immediate vicinity of the accretion disk of the GN. And then it shocks against the interstellar medium and accelerates the swept-up gas and producing the galaxy scale outflows. And for the kinetic power, we know that it is proportional of the third power of the velocity. So large velocities imply large kinetic energy. And for an efficient feedback mechanism, the kinetic power should be a few % of the bolometric luminosity. So to look at the feedback of the AGN at its extreme, we know that the most luminous quasars are the ideal targets for to search for powerful AGN-driven outflows. In particular, at the cosmic noon, which is at redshift range of 1.5, 3.5, which is also the peak of both star formation and quasar activity. And as a result of cross correlation of SDSS type 1 AGN and WISE catalog, we collect a sample of 85 hyperluminous quasars, type 1 quasars, with bolometric luminosity larger than 2 per 10 to the 47 erg per second. As you can see here in this plot, the WISH quasars are the red stars. And focusing on the broad absorption line outflows, we know in the UV, we know that they are observed in 50% of the quasar population. And the bulk of velocity in such outflows are around 3,000, 25,000 kilometers per second, but they can reach up to a few % of the speed of light. And for the WISH quasars, we found a larger fraction of broad absorption line outflows with larger barnicity index, which is the measurement of equivalent width in kilometers per second. And also I have a higher velocity of the outflows. So we can say that broad absorption line outflows are more and faster in hyperluminous quasars. Focusing on a particular WISH quasar, the J1538, which is a broad absorption line AGN at redshift 3.5 with bolometric luminosity of 6 per 10 to the 47 erg per second, a black hole mass of 6 per 10 to the 9 solar masses, and accreting near Eddington. We found for these quasars that show outflows at those scales in the broad layer region by looking at the blue shift of the carbon-4 in the narrow layer region from the blue sheet of the oxygen tree. So this means that we have outflows at the kiloparsec scale, but also we found outflows also at the CGM scale by looking at the nebular Lyman alpha. Thanks to MUSE observation, we found outflows nearby 13 kiloparsec. But as I said, this is classified as a BAL, but looking at the spectrum, we found that the carbon-4 does not show absorption, but we found absorption blueward of the silicon-4. And actually, broad absorption line usually show both absorption in carbon-4 and blueward of silicon-4. So we associated this absorption to carbon-4 since in general, there are no objects with silicon-4 absorption without the corresponding carbon-4 absorption at similar velocity. And so we can classify this object as ultra-fast outflows broad absorption line. And this is important since a monitoring of such object can help in identifying the acceleration mechanism and also the structure of such outflows, which are poorly constrained. In particular, we have two observations of SDSS and proprietary data as Lyà and MUSE, LBT mods, and Subaru Focus, with the time separation between the two SDSS spectra is the longest one, and the shortest one is between the MUSE and mods observation. Here you can see a comparison of the 5 spectra at different observation epochs. You can see these 3 different systems, ultra-fast systems. In particular, for the hetero, we can see that it varies in a smooth way, and B and C throw actually vary both in shape and strength. And in particular, as you can see here, from the first epoch here in blue up to the last one here in pink, the BLL outflows actually disappear in this last observation. So it's highly variable. We measure the outflow velocity, as you can see here, for the three systems, which are in the range of 0.13, 0.80 in unit of speed of light. We consider and study the variability of such outflows. We measure the volumicity index, and here you can see its variation as a function of the different observation epoch. In particular, here you can see that the B and C throw vary in concert and in a similar manner. Instead, the hetero show a different behavior. So this means that actually the variability mechanism can be different for this throw. But what is the cause of variability? It could be the change in ionization of the motion of the gas transfers to our line of sight. So,
1 minute, Giustina.
Thanks. So we look at the first 2 epochs and or the ions at different ionization state. Focusing on the B and C throw, we found that the silicon 4 ions is almost stable. Instead, the carbon 4, nitrogen 5, and lemon alpha are variable. This is inconsistent with the gas motion scenario, and so the change in ionization is favored. Instead, for the hetero, we can see that the variation is similar. This is consistent with gas motion. We put constraint on the location of the BAL location, which is around 36 parsec. But also we used since this outflow is variable also during the 2 epochs with the shortest variability time, we put a more stringent constraint on the radius around 0.7 parsec, which is the size of the broadline region. And this is consistent with the theory that put the location of the BAL with co-spatial or just beyond the broadline region. So we derived the kinetic power of such outflows, assuming an expanding shell at a certain velocity and covering factor. Here you can see in red the kinetic power by assuming the radius as 36 parsec, and here the radius of 0.7 parsec. As you can see, this is one of the most powerful ultrafast outflows. Indeed, is comparing with the X-ray UFOs and also other outflows in ionized phase and the other BAL. But also the kinetic power is a few percent of the volumetric luminosity, so also have an efficient, could have an efficient mechanism on the host galaxy. So just to recap, we discover a powerful and variable outflows with appearing and disappearing of such features. And these ultra-fast outflows observed in UV are easy to observe, and also we can study their variability with routine observation, and also are observed in more than one line, instead of, in contrast to the X-ray UFOs, which are required time-consuming observation and also are typically observed in just one line. Up to now, they are limited in number since the BL outflows are searched up to velocity of 25 km/s, but as you I've seen these outflows can reach up to 60,000 kilometers per second. There is a first systematic study of such UFOs by Rodrigo Hidalgo 2020, which discovered 0.6% of such ultra-fast outflows, and in the WISH survey we discovered 5% of these UFOs. And we also planned a monitoring of high resolution instrument to study the variability in timescale of the months, but also constrain the column density and put stringent constraint on radial distance and kinetic power. Thank you.
Thank you, Giustina. We have maybe time for one quick question. I see Christopher Agostino. I don't know if no. Okay. Otherwise, Manda Banerjee asking the Q&A chat. Thanks you for the talk, and she asks, do you have multi-epoch photometry for this quasar to get a handle on how the broadband SED might vary on similar timescales as traced by your spectra?
Yeah, actually we do not have, because it could help in disentangle also between different mechanisms, but no, we don't have.
Okay, thank you very much. I think we can move on actually to the next talk, since we are a little bit behind the schedule. Fengwu soon. Thank you. Excellent.
Okay, thank you. Can you hear me?
Yes, I think it's okay.
Okay, thank you.
You can go ahead.
So hello everyone, my name is Fengwu. I'm a fourth-year PhD student at the Stewart Observatory, University of Arizona. My advisor is Dr. Ichi Igami, and I would like to thank the organizing committee to give me the opportunity to talk about our recent work, which is based on the ALMA lensing cluster survey, a 100-hour ALMA large program. Today I will going to talk about the far-infrared properties of normal dusty star-forming galaxies across redshift 0.5 to redshift 6. 1 second. Okay, so first of all, I would like to talk about what are normal dusty star-forming galaxies and why they are important. Over the past 2 or more decades, people have already found the population of dusty star-forming galaxies at about redshift 1. However, most of them are so-called Euler galaxies with IR luminosity greater than 10 to the 12 solar luminosity, and with star formation rate greater than 100 solar mass per year, which means they are extreme and rare objects. The more normal galaxies, Lurk-like objects, has star formation rate between 10 to 100 solar mass per year. The far-infrared properties of these galaxies have been poorly characterized at about redshift 1 because of the general shallowness of submillimeter data until today. So one advantage that we could take is the gravitational lensing effect by massive galaxy cluster in the front. For example, on the right-hand side of this plot, I'm showing the HST true color image of one of the cluster field, which is called RXCJ0032. That is one of the 33 ALCS cluster field that our program has been observed. So now you can see the lensing critical curves at the redshift 3 showing the magenta solid line, and also massive galaxy cluster members in the field. Most of these galaxies are quiescent galaxies, so they are very low in dust content, which makes the cluster itself almost transparent at 1.2 millimeter in the ALMA continuum, which is shown on the left-hand side. The background dusty galaxies are therefore lensed and magnified, which makes it easier for us to detect intrinsically faint galaxies that are not easy to be detected within a blank field. Oh, give me a second. Okay, so now we have the ALMA lensing cluster survey. Here we have, I'm showing 144 continuum sources detected with our 100-hour program. ALCS studies 33 lensing cluster field with a 100-hour with a total survey area of 134 square arc minute, and the wavelength is at 1.15 millimeter. All of this cluster field has been observed by HST tracery programs like Frontier Views, Clash, and Relix. In total, we detect 180 sources, including 141 sources that are securely detected above 5 sigma, and also 39 sources detected based on prior catalog using HST and IROC data at about 4 sigma. A few papers have been published, and my work focus on the fine infrared properties has been submitted recently. We will also submit the source count paper very soon, led by Seiji Fujimoto et al. At the Cosmic Dawn Center, and that will provide the best characterization of the millimeter source count function in present days. Here on the left-hand side, I'm showing the IR luminosity function. IR luminosity versus the redshift of ALCS sources. Spectrum confirmed sources are shown in the black symbols, and the open symbols are for the Z-only sources. The values shown here are all corrected for lensing magnification factors, which is indicated by the gray vertical bars shown here for each of the sources. One unique advantage of our program is we could use lensing magnification to break through the confusion noise limit in control band, which is shown by the black dotted line here. 40% of the sources detected here are intrinsically fainter than the nominal detection limit. In other words, these sources cannot be detected in any blunt cosmological deep fields with Herschel. And you may also notice red squares over here. The square is in the region that ALMA data is deeper than the Herschel data. This is the stack of 12 optical near-infrared dark galaxies that are not detected by Herschel band, which includes, in this population, we detected at least 2 so-called IROC galaxies. Basically, they are only detected in ALMA bands. And similar sources has been discussed by paper like this, Fujimoto et al. 2021, which is a Nature paper. So these sources could reside at about redshift 6. And almost cycle 8 CO lens scan observation has been scheduled for these 2 sources. And the other sources are mostly HST H-fin sources, which similar sources has been discussed by Wang et al. 2019, which is also a Nature paper. And recently, we also have a similar work discussing this object listed here. And in this plot, I'm showing the best available redshift distribution of our sample as a function of lensing corrected millimeter flux densities. So the magenta circle here shows represent the medium redshift of sources, ALCS sources, about given flux densities at 1.1 millimeter. And the blue diamonds are similar measurements from the literature. And you can see that towards faint end, for the faint millimeter sources, around or below 0.1 millionsky, they are dominated by galaxies at a redshift of around 1 to 2. The medium redshift as a function of millimeter flux density is very close to 1. One of the models given by Kathleen Kesey's group in 2018, in which they suggest decreasing dust obscure fractions of cosmic star formation rate densities at about redshift 4. So this plot shows the dust temperature versus the IR luminosities of sources in both local universe, including the gold samples, kingfish samples, and also at the high redshift, including AS2UDS survey, SPT, and the study samples. For a long time, people have identified such kind of positive correlation between the 2 pieces of quantities and use it as cornerstones for photosys or IR luminosity estimate. And the lurks at high redshift are found to be cooler than their local analogs. In our survey, we also find that the lurks with IR luminosity greater than 10 to the 12 solar luminosities are cooler than those in the local universe. However, for lurks with IR luminosity between 10 to the 11 to 10 to the 12 solar luminosities, we don't see clear difference between their dust temperature and those of their local analogs. So this plot shows the redshift illusion of dust temperatures. We discussed the sources in 2 beams, the 2 luminosity beams, the lurks beams and also the U-lurks beams. The gray shaded region here means the parameter space that our survey is not very complete. For the lurk sample, you may be able to identify a weak positive correlation between the T-dust and the redshift. But the p-value to rule out the monotonic relation is only 0.06, which is slightly above the 5% threshold. So we cannot claim any correlation here, sadly. Regarding the U-lurks group, it's clear that there's no correlation between the dust temperature and the redshift. And we also know that the dust temperature is well correlated with gas division timescale. For example, we know compared with the lurks, U-lurks are higher in dust temperature, so they are lower in the gas division timescale. shorter in diffusion timescales. Therefore, we can also draw a conclusion that no redshift dependence of gas diffusion timescale can be found for IR luminosity complete sample from redshift 1 to redshift 4. So that's everything I want to show today, and here are the summary of takeaway takeaway message. Thank you.
Thank you very much. Maybe we have some questions from the audience. We don't have any questions yet from the Q&A. Maybe if yeah, I can ask a question actually if nobody has one. From the models, when you compare with the models, the redshift as a function of so are these models with which you compare have a you say, for example, dust rich versus dust poor? Do they have I assume these are semi-analytic models, right? Do they have some dust growth built in them, or some kind of chemical evolution in order to
I believe their model is
metallicity?
I believe their Castelli-Cassis model is based on the source count function, and they assume some evolution of the IR luminosity function shape, and they propose two extreme scenario where the high redshift and the IR luminosity function, the growth of that is very slow, and that's the dust rich. So that means redshift 4.5 is close to redshift 2. And for dust poor, the growth of the IR luminosity function is very fast. That's my understanding of their theoretical model. I don't think chemical evolution is a very important factor in their models. That's my understanding.
And we are talking about an order of magnitude difference in metallicity, or something much larger.
You mean for the
between the dust rich
ALCS?
Yeah. Is it a factor of 2, a factor of 10? I don't know.
I don't think that's the reason that could cause the different models may be related to the metallicities, but in their models, I don't think metallicity is really a factor that people tweak there. It's just like you assuming the evolution of the IR luminosity function slope, and also the characteristic luminosity, and that's all. Yeah. If you ask about the metallicity evolution of ALCS sources, I can only say that's something in progress, and you can stay tuned.
Okay, thank you very much for the answer. If anyone has any other question, please post it in Slack, and we can go for the last talk of the session by Zhefu. Maybe you can start sharing.
Okay.
Excellent. Zhefu will talk about black hole masses from the OzDES reverberation mapping project. Take it away.
Okay. Hi, everyone. I'm Zhefu, a graduate student in the Ohio State University. And here I'm going to talk about the black hole mass measurements from the OzDES reverberation mapping project. So the supermassive black holes commonly exist at the centers of massive galaxies. And it is an interesting topic of how the supermassive black holes evolve over cosmic time. And in order to study the evolution of supermassive black holes, a critical parameter is the mass of the black hole. And beyond the local universe, the most accurate method to measure the black hole mass in AGNs is the reverberation mapping method. And here shows an example of how this technique works. So the typical spectra of type 1 AGNs contains a blue power law continuum coming from the accretion disk around the central supermassive black hole. And the continuum ionizes the gas cloud in the broad line region, which produces broad recombination lines. Both the AGN continuum and broad lines are variable with time. And there will be a time delay between the variation of the continuum and broad lines due to the light travel time from the accretion disk to the broadline region. Therefore, this time delay indicates the size of the broadline region. And according to the Vero theorem, we can use the broadline region size and the width of the broadlines to calculate the black hole mass. And in order to measure the time lag between the agent continuum and broad lines, we need to monitor the targets for some years to derive the light curve of the continuum and the broad lines, as examples shown in the left figure here. We then derive the probability distribution of the lag between the light curves, as the example shown in the right figure. And here it shows the lag signal around a year. If we look at the light curve, in fact, we can notice this 1 year time delay between the light curves by eyes. And to make this more clear, the red data points in the lower panel shows the continuum light curve that are shifted by this 1 year time delay. And here the shifted continuum can well match the line light curve, which verifies the reliability of this time delay signal. However, it is observationally expensive to measure this time lag because we need to monitor the targets for years to derive the light curves. And an important finding in previous reverberation mapping studies is a strong correlation between the broadline region radius and the agent continuum luminosity. And this RL relation allows us to estimate the broadline region radius and calculate the black hole mass using just a single epoch spectra. And this method is much more efficient and allows us to calculate the black hole mass for large samples of agents. However, in early reverberation mapping studies, most of the time lag measurements were limited to low redshift and low luminosity agents, as shown in this figure here. And in those studies, the RL relation was constrained using only the H-beta line, while the RL relation for the magnesium-2 and carbon-4 line were poorly constrained. It would be important to further constrain the RL relation for the magnesium-2 and carbon-4 using more lag measurements, because those RL relations are the key to the single epoch black hole mass estimates at higher redshifts. And this motivates some industrial scale reverberation mapping campaigns with large sample and long monitoring baseline. There were 2 large campaigns that started around similar times. One is the Sloan reverberation mapping project based on the Sloan survey, and the other is the OzDES reverberation mapping project based on the dark energy survey. And this figure shows the footprint of DES. And in our reverberation mapping project, we monitored about 800 quasars for 6 years. We have about weekly photometry from DES and have about monthly spectroscopy from the OzDES survey. And in this talk, I will focus on the magnesium-2 reverberation mapping that I have been working on. And in the recorded version of the talk, I will also include the carbon-4 lag measurements led by Andrew Penton in University of Queensland. I will also include some details of the data analysis and the continual reverberation mapping results in my previous works, and also some simulation works for the survey design led by Uman Malik in the Australian National University. Here shows examples of the figures that I will discuss in the recorded talk, and please take a look at it if you are interested in those topics. So in my most recent paper, we are excited to publish our initial measurements of the magnesium-2 lags. And in this paper, we measure the magnesium-2 lags for 9 quasars. And here we show them in the RL relation plot. namely the correlation between the broadline region radius and the agent continuum luminosity. Here's okay, thanks. And here the blue squares shows our measurements. And here most of our measurements are inconsistent with both the H-beta and magnesium-2 RR relation from literature. And these initial measurements were only based on the first 5 years of data with only part of the OzDES sample. And now I have finished the analysis of the full OzDES sample after adding the year 6 data. And it is exciting that we were able to obtain a large sample of new magnesium-2 lag measurements. In this figure, we show the preliminary measurements for the magnesium-2 lag for 27 quasars. And this sample is a significant addition to the RR relation of magnesium-2. With this sample, we expect to derive the best constrained RR relation for the magnesium-2 line to date. So in summary, in our project, we monitored about 800 quasars for 6 years, and we expect to have one of the largest sample of the magnesium-2 and carbon-4 lags and the corresponding black hole mass estimates. We have published some of our initial results, and there will be more to come out in the near future. Okay, thanks for your attention, and I will take questions.
Thank you very much, Zhefu. On time, exactly. I don't know if we have, yes, we have one question from Paulina in the Q&A. How does the dispersion in the magnesium-2 sample compare with the H-beta relation?
That's a good question. So in theory, the magnesium-2 line is a collisionally excited line, which is expected to be somehow different from the Balmer lines like H-beta. And observationally, as found in the previous results, the scatter in the magnesium-2 RR relation is significantly larger than that in the H-beta RR relation. And also, according to our sample, we can also notice some significant scatter, which is kind of large relative to the H-beta. So does this answer your question?
Probably yes, although Mari-Lori Martinez Aldama has a related one. First, she thanks you for the talk, and she asks if it's possible to propose a magnesium-2 radius luminosity relation with the new data.
I'm not sure whether I understand this correctly. Yes, so
probably she's asking about in relation with the scatter, right? If you believe that there is a relation, and to what extent it can be used as a calibration.
Yes, so as we say, currently the results still have large scatter. And this is the reason that we want more magnesium-2 lag measurements to determine whether there's really a good correlation and to further constrain the intrinsic scatter of the correlation, if the correlation exists. And currently our measurements are still preliminary, and we also plan to do some more homogeneous reanalysis of the literature results. And hopefully after we complete our analysis, we will have a better answer to this question of the existence of the RR relation and its scatter.
Okay, thank you very much. Maybe I think the question from Marianne Vestengard is related to what you have answered already. So I think I'm gonna jump to the last one. It says Sarah Rosebrough, sorry. Very interesting talk. Do you know if a similar study has been done with SDSS data? And if so, have you compared your results?
Yeah. So the Sloan survey also have published their lag measurements on the magnesium-2 and also other broad emission lines. For example, the green data point in this figure here comes from previous results from the Sloan reverberation mapping survey. And here we can, in the Sloan reverberation mapping paper, they do find a quite significant scatter on the RR relation. And in our case, at least for our preliminary results, the scatter seems to be not so significant, but we need to, until our final analysis to see how it really compares between the two.
Okay. Thank you very much, Zhefu, again. And you can check if you want give more detailed answers to other questions posted in the Q&A. You can check in the Slack to give more detailed answers. So I think we are done. I want to thank you all the speakers for their very nice talks. And I think now we have a 15-minute break, 10-minute, 15-minute. I don't know if Roberto or Jorge want to say something. In theory, it was 20 minutes, but we are 10 minutes late. So
I would say let's give 15 minutes to everybody. So instead of coming back at 10:40 Eastern time, we'll start at 10:45 Eastern time.
Excellent.